In the previous video, we discussed about charge, we discussed about the definition of charge and the nature of interactions, nature of forces between charged particles, and we also saw whether charging is possible using some simple methods or not. We actually saw some of those processes of charging, and in today's video what we will be doing is we will be discussing nature of forces between charged particles and the magnitudes of those forces, as well as the effect that the medium surrounding the charges has on those forces. Now, the law governing force between charged particles is called Coulomb's law, and Coulomb's law is essentially about forces between charged particles. Now, charged particles are what one might call point charges. Now, with point charges, one has to be aware that there is really no such thing as an ideal point charge, because we cannot assemble charge at a point. But what we can do is, if we take small spherical charged objects like the ones I have shown here, they can be approximated, they can be assumed to be, they can be imagined to be nearly point objects. So we have 2 point objects, or 2 small tiny spheres having charges q1 and q2 placed at a distance r from each other. Now, if they are like charges, they will repel along the line joining them, and if they are unlike charges, they will attract each other, they will exert attractive forces F each on each other along the line joining them. The forces which 2 charged objects exert on each other will always be equal and opposite, and that's easy to guess. That's Newton's third law. So if 2 objects are exerting forces on each other, they have to be of the same nature and they have to be equal and opposite in direction. Now, if they are, as I said, like charges, they repel. If they are unlike charges, they attract, and the forces will always be along the line joining these charged objects. The magnitude of these forces is directly proportional to the product of the 2 charges and inversely proportional to the square of the distance between these charges. Now, that's the law that governs forces between charged objects. The proportionality can be converted into an equality by introducing a constant, and for the time being, let's call this constant as capital K Q1 Q2 by R square. Now, if these charged objects are placed in vacuum or in free space for charged particles in free space, now free space as in free of matter. So we are talking about space which is free of matter, which basically means vacuum. If we have charged objects, charged particles placed in vacuum, then the value or the magnitude of this constant will be 9 into 10 to the power 9 Newton meter square per Coulomb square. Coulomb, I introduced Coulomb as the unit of charge in the previous video. Now, this K is often expressed in a slightly different form. It's expressed as 1 by 4 pi. Now, pi is your usual pi, epsilon naught, where epsilon naught is a constant, universal constant in nature. It is described as permittivity of free space. This epsilon naught is permittivity of free space, and it equals 8.85 into 10 to the power minus 12 per Newton per meter square Coulomb square. So that's epsilon naught for us, the constant which we call permittivity of, again, free space. As I said, the law that we have discussed so far is for charges placed in vacuum or in free space. Now, the law can be carried a little further in what we call the superposition principle. Now, what is superposition principle? Well, this principle says that force on a charged particle due to another particle is independent of all other charges in their neighborhood. So, if we have a charge, let's say Q naught, and a charge Q1 in its neighborhood exerts a force F1 on it, this F1 is completely independent of the presence of all the other charges in their neighborhood. So if there is a Q2 and a Q3 and a Q4 in that neighborhood, the force exerted on Q0 by Q1 does not change because there are other charges around them. So this particular principle is called superposition principle. We will discuss a little more about this. Essentially, it is about independence of forces between two charged particles on the presence of other charged objects in their neighborhood. So let's imagine that we have a charged particle over here, Q0, and a charged object, Q1, exerts a force, F1 on it. Let's say this is F1, exerted on Q0 by Q1. Now, if there are other charges here, let's say Q2 and Q3 and so on and so forth, now these charges might exert their own forces on Q0, but their presence or their absence has no bearing, no impact on the force F1 exerted on Q0 by Q1. And that's your superposition principle. So the force exerted on Q0 by Q2 is, let's say, F2, and again superposition principle applies. The force on Q0 due to Q2 has no is not affected by the presence of all the other charges in this neighborhood. Similarly, Q3 might apply its own force, let's say F3, and Q4 might apply its own force, F4, and so on and so forth. All these forces are calculated for a given pair of charges. So F1 is exerted only by Q1, F2 is exerted only by Q2, and so on. Now, you have a number of forces acting on Q0 because of the presence of the neighborhood charges. Now, obviously, the net force on Q0 will be the vector sum of all these forces. Forces being vectors have to be added and subtracted like vectors. So the force on Q0, net force on Q0, is a vector sum of F1, F2, F3, and so on and so forth. Remember, when you calculate F1, you are looking at the interaction between Q1 and Q0 alone, and you're not really bothered about the presence of other charges. They do not have any impact on the force on Q0 by Q1. And therefore, the net force on Q0 is the vector sum of the forces exerted on Q0 by all the individual charges. This then is our superposition principle. Now, coming to the presence of medium around charges, forces in the presence of material medium. Now, when there is a material medium present, interesting things can happen. Now, in our previous video, we discussed that charged objects can induce charges on material objects placed close to them. And the same thing will happen here. So if we have a charged particle and we have a medium around it, there will be an induction effect on the medium. There will be induction of charges in the medium, and once charges get induced on the medium, we say that the medium has been polarized. Now, this polarization leads to induction of charges in the medium, and these induced charges then start applying their own forces on the charged objects, thereby having an impact on the net force that the charged particles experience, even though the force that the charged particles exert on each other remain unchanged. Now, let me explain this. Let's consider two charged objects, Q1 and Q2, placed at a distance r from each other, and we have placed them inside a very large lake, let us say, of kerosene oil or some such oil. So we have two charged objects, Q1 and Q2, two charged particles. For simplicity, let's assume that both these charged objects are actually positive. So these are two charged objects, they are positive, they carry positive charge, and we have placed them right in the middle of a very large lake of oil. Now, so we've got these two charges, two charged objects, Q1 and Q2, placed at a distance r, deep inside a lake of kerosene oil or some kind of oil. And these two charged objects will obviously repel each other by applying a force 1 by 4 pi epsilon naught times Q1 Q2 by r square. This force, which the charges exert on each other, will remain unchanged. Now, the force that the charged particles exert on each other does not change, but what happens, however, is that, as you recall, that we have placed them deep inside a lake of some oil, and what happens when you keep a material object close to another charged object? Well, the near side of that material acquires a opposite charge. That is, in this case, since Q1 was positive, the surrounding oil will acquire a negative charge. Of course, the oil will acquire an equal and opposite charge, that is positive charge on the other side. When you place a positively charged object near an uncharged object, then the near side becomes negatively charged and the far side becomes positively charged. But here the far side is very, very far away because it's a deep, large lake. So there will be some equal and opposite positive charge induced, but that will happen very, very far away at infinity. And that positive charge has no influence over here. Therefore, what happens is this charge Q1 has exerted a force F on Q2, and Q1 exerts a force, so the induced charge here, the green negative charge, applies a force Fi. This is the force due to the induced charge. So Q1 has exerted a force F on Q2. That force is given here. Now Q1 has induced a negative charge in the surrounding medium, and the negative charge has exerted an attractive force on Q2. The net force on Q2 therefore has undergone a decrease. The net force now will be F minus Fi. The net force now is F minus Fi. So there is a reduction in the net force exerted on Q2. An identical effect will take place on the other side. Q1 will also experience a reduction in the net force acting on it. Now this net force can be calculated using a modified version of the Coulomb's law. And now what we'll say is it's directly proportional to the product of the charges, no change there, inversely proportional to square of distance, and we will have a constant here which is somewhat modified, 4 pi epsilon r times epsilon naught. Now the epsilon naught is your familiar constant of permittivity of free space. Epsilon r here is a constant for the material in which the charged particles are immersed. It is called the relative permittivity of the medium. Another common name for this is dielectric constant of the medium. Now the net force always undergoes a reduction. The net force will be less than the original force F, and therefore epsilon r has to be greater than 1 for all materials. So any material medium will have an epsilon r greater than 1. For typical insulating materials, epsilon r will be say between 1 and maybe 20, 30, 40. And for conductors, epsilon r can have fairly large value running into several hundreds. Theoretically, a conductor is supposed to have an infinite magnitude of epsilon r, and therefore the net force that is exerted on charges placed in a conducting medium should be 0. More on conductors in some later videos. But this then is the modified version of Coulomb's law. Now remember one very, very important point, that this doesn't work all the time. This works only under specified conditions. And the specified condition that I'm talking about is that the material should be spread all the way up to infinity. If material is not spread all the way up to infinity, this does not work. So it's a fairly limited kind of a formula here. It cannot be used in absolutely all kinds of circumstances. You know, for instance, I have seen certain authors who place a slab in between a dielectric slab and then use this result to calculate the net force on the charges. It is absolutely incorrect. Such calculations are not possible. This formula, as I said, works only when the medium is spread all the way up to infinity. And why? Because we have made the assumption that there is this negative charge induced and there is some positive charge induced, but the positive charge induced is at infinity and therefore has no effect in this vicinity. This assumption will not work if the medium is not spread all the way to infinity. So please remember that this cannot be used indiscriminately, only when the medium is spread all the way up to infinity. Now we've understood Coulomb's law and we have understood the modification that it goes through in a material medium. We can now have a look at some simple applications of the ideas learned so far. But before I proceed further, I would like to state an important point here, and that is that if you have 3 or more non-collinear point charges, if you have 3 or more non-collinear point charges, the system comprising these charged particles cannot be in equilibrium. Stable equilibrium of a system of 3 or more non-collinear charges is not possible. So always remember this. This is some well-known theorem. I do not quite remember the name of the author of the theorem, but you do need to remember the theorem. If you have 3 or more non-collinear charges, then the system comprising these charges cannot be in any kind of stable equilibrium. Now what we'll be doing is we will be taking up a few very simple examples on forces between charged particles, Coulomb's law, etc. Some very basic kind of problems. To start with, there is this problem we'll discuss about 3 charged particles being in equilibrium. Now remember, if we have 3 or more charged particles, their equilibrium would not be possible if they were non-collinear. So they have to be collinear for equilibrium to happen. So now let's visualize a simple problem here. We have a charged particle carrying a charge Q and plus Q, and we have another charged particle here at a distance d, let's say, and this charged particle has a magnitude plus 4q. The distance between these charged particles is, let's say, r. Now these 2 charged particles are separated by a distance r. One of them is plus q, the other one is plus 4q, and we now asked the question. The question says, where on the line joining them, this line here, where on this line should we place a third charged object so that the system of the three charges is in equilibrium. So we have a system of two charges already. We have to place a third charged particle somewhere on this line so that all three of them are in equilibrium. Now, since you already have two positive charges repelling each other, the third charge would have to be negative. So that much we can figure out immediately, that the third charge has to be negative. Now, we have to calculate the location of that third charge. We have to figure out the location of that third charge, and we have to calculate also the magnitude of that third charged particle. So we are looking to locate a charged particle somewhere on this line, which ensures that all three charged particles are in equilibrium. We are also asked to to locate it and to calculate the magnitude. So that's your question. Now, since we already figured out that the third charge has to be negative, can we place it somewhere here? Now, let's divide the entire line in three parts. One to the left of this plus q, then the second region in between these two charged particles, and third region to the right of 4q. Now, can we possibly place that negative charge over here? Now, if you place that negative charged particle over here, both these positive charges will attract it towards the right. So both forces on that third charged particle over here, let's say this third charged particle is Q1 and it is a negative charge. The forces which are exerted by these two charges will be both towards the right. Since both the forces are in same direction, their vector sum cannot be 0, and therefore this charged particle cannot be in equilibrium if placed here. So this position is ruled out. Can we now place this minus Q1 somewhere over here? Again, we run into the same kind of a problem. If this minus Q1 is placed here, both these positive charges will exert attractive forces on it, and both those forces will be towards the left in the same direction. So the forces on Q1 over here were towards right, and their vector sum could not be 0. The forces here are towards the left, and their vector sum cannot be 0. So these two positions are ruled out, which leaves us with this space between the two charged particles. So what we do is we decide to place this minus Q1 charge over here at a distance x. This is where we place it. Now this distance is x, and therefore this remaining distance is r minus x, and we're now going to have a look at the equilibrium of these three charged particles. And looking at the equilibrium, we'll be able to calculate x, and also we'll be able to calculate the magnitude of Q1. Now let's consider the equilibrium of this charged particle Q1. Now let's look at Q1. This here is Q1. Now for Q1, this plus Q exerts an attractive force towards the left. Now let's say this attractive force on Q1 towards the left is 1 by 4 pi epsilon naught times Q into Q1, Q1 by x square, correct? Q1 also experiences an attractive force towards right because of 4Q here. This is negative, this is positive, so there's an attractive force. This will be towards right. I'm depicting it here. And it will be having a magnitude 1 by 4 pi epsilon naught Q1 times 4Q by square of this distance r minus x whole square. Now for equilibrium of Q1, these forces must have a zero resultant. These forces are already in opposite direction, and for zero resultant it is essential that they have the same magnitude. So they already have opposite directions. If their magnitudes are equal, the resultant will come out to be 0. So equating these magnitudes, we get 1 by 4 pi epsilon naught Q1 by x square equals 4Q Q1 by r minus x whole square. So that's the equation showing equal magnitudes of these forces. Q1 cancels and we have r minus x by x whole square equal to 4. Now we take an under root on both sides and we get r minus x by x equals, now when you take an under root of 4, you get plus 2 as well as minus 2. So if you take minus 2, then you have r minus x by x equals minus 2, and therefore r minus x equals minus 2x. X therefore comes out to be minus r. Now what would the minus sign imply? The minus sign implies that x is not towards the right of q but towards the left of q. We've assumed x to the right of q. Minus sign indicates that the direction of x taken is wrong. It is to the left of q. But then left of q space was already ruled out. What does this root of the equation suggest? What it suggests is that at a distance r to the left of q, if we place this q1, the magnitudes of the forces due to q and for q on q1 will be same. But even though the magnitudes will be same, the forces will be directed in the same direction and the resultant cannot be 0. So this just tells us that the magnitudes of the force on q1 due to q and for q will be same if we place q1 at a distance r to the left of q. But at that location the net force cannot be 0 because both forces are in same direction even though they have the same magnitude. So we rule out this root of the equation. We look at the other root, r minus x by x equal to plus 2. And so we have r minus x equals 2x, and so r equals 3x and x equals r by 3, which is acceptable because x being positive indicates that q1 is to the right of q. Also, the magnitude that we are getting is less than r, so we are not going beyond 4q on the right side, which again we had ruled out. So this is what we were looking for. So we have to place this q1 at a distance x to the right of the charge plus q. We figured out the magnitude. The next thing to do now is to figure out the magnitude of this charge. We figured out the distance. We have to now figure out the magnitude of charge. Now to figure out the magnitude of charge, we have to examine the equilibrium of either one of these two charges. So let's look at q here. Now this q experiences a repulsive force from 4q. That will be to the left, 1 by 4 pi epsilon naught 4q into q, we have 4q square by r square, and this q will experience an attractive force towards the right due to minus q1, and this one will be 1 by 4 pi epsilon naught q times q1 by the square of the distance x. Now we already know x is r by 3, so r by 3 whole square. Now if you put an equality sign between these two forces and then solve for q1, you end up getting q1 equal to 4q by 9. And we have already figured out, that q1 has to be a negative charge, so we indicate that here. q1 has a magnitude 4q by 9. It's a negative charge and has to be placed at a distance x to the right of q, and the magnitude of x is r by 3. A very, very simple problem this. Now let's take up another example on Coulomb's law. I hope you've understood, and maybe you can take a screenshot and take notes. We move on now to the next problem on this. Another very simple problem. Let's say we have a charged object carrying a charge q, and we are interested in splitting it up into two parts, not necessarily equal. We are interested in splitting it up into two parts and then placing them at a specified distance L from each other. Now the question is, what should be the magnitude of each one of these parts so that the force of interaction between these two parts is a maximum. So let's say we have split this up into two parts. One of them has a magnitude q, and the other one, of course, as per conservation of charge, will be capital Q minus small q, and we have placed them at a distance L. Since they are like charges, they will repel by applying equal and opposite forces. The problem is, the question is that we have to figure out the magnitude of small q so that this force is maximum. This distance is fixed, so that's the problem defined. We have a charge capital Q. It is to be split into two parts which should be placed at a specified distance L. Now the two parts should be such that the force of interaction between them is maximum. Now we have to figure out the magnitude of small q. Once again, I've defined the problem. Now let's look at the solution. The force of interaction between these two parts will be 1 by 4 pi epsilon naught times q into capital Q minus small q by L square. And we have to figure out the maximum magnitude of F and the magnitude of Q, small q, for which F is maximum, all other things being constant. Now, you will easily be able to recall one of my earlier classes on differentiation, where we learned to calculate maxima and minima. The maxima of this force will occur when the derivative of F with respect to small q is 0. You will notice this F is a function of this q here and f will be maximum or minimum when the derivative of this quantity with respect to q is 0. So now look at this f here. It is 1 by 4 pi epsilon naught L square. This is constant, and here we have small q into capital Q minus q square. This is f. Now f will be minimum when its derivative, minimum or maximum when its derivative is 0. Let's calculate its derivative. Df by dq, we get 1 by 4 pi epsilon naught L square. The constant remains the way it is, and we get capital Q minus 2q. And so this is the derivative. For maxima or minima, the derivative has to be 0, and therefore small q comes out to be capital Q by 2. So derivative of f is 0 when small q equals capital Q by 2. Now whether we have a maxima here or a minima, for that we have to have the second derivative. Now the second derivative, d square f by dq square, will be equal to 1 by 4 pi epsilon naught L square. Capital Q is a constant, the derivative is 0, minus 2q, the derivative is minus 2, and so we have a negative double derivative. Since it's negative, what we get to know is that there is a maxima at small q equal to capital Q by 2, and therefore the maximum magnitude of the force will be equal to 1 by 4 pi epsilon naught. In place of small q we have capital Q by 2, so capital Q minus capital Q by 2 divided by L square, and so the maximum force now is Q square by 4 pi epsilon naught times 4 L square. Yes. So that's the maximum force of interaction between these two charged particles. So what we've learnt in this video is we've learnt about Coulomb's law, and we've learnt about how it gets kind of modified when we place charged particles in a material medium, and we've taken a couple of very simple examples about forces which act on charged particles when they're placed close to each other. We've learned the superposition theorem or the superposition principle. So we now are at a point where we can study the more serious applications of this Coulomb's law and the concept of forces between charged particles. More on all these things in the upcoming videos. Thank you very much.